Hello guys, my name is R. Joseph Cesar Sundar Kumar from first time physics. Today we are going to talk about Schur's lemma 1 and 2. Let's get into it now. There are two theorems of fundamental importance which go by the name of Schur's lemma and which are extremely useful for the study of the irreducible representation of a group. They also lead to the orthogonality theorem of the irreducible representation, and we shall consider them. It is assumed that the space in which the representation are defined is a complex vector space. If gamma I is an irreducible representation of a group G, and if a matrix P commutes with all the matrices of gamma I, then P must be a constant matrix, that is, P is equal to C E, where C is a scalar. We shall prove this lemma by two methods. First proof. Let A be any element of the group G, then it is given that gamma I A P is equal to P gamma I A for all A belongs to G. If the dimension of gamma I is n, P is a square matrix of order n. Since it has been remarked that the matrices of representation can be taken to be unitary, it follows that each of the matrices gamma A, gamma B, etc. possesses a complete set of n eigenvectors. Since P commutes with gamma A, etc., it follows that P also has n linearly independent eigenvectors. Let xj be eigenvectors of P with eigenvalues Cj. Then we have Pxj is equal to Cjxj. Multiplying both sides from the left by gamma ia, we get gamma ia Pxj is equal to gamma ia Cjxj. P gamma ia xj is equal to Cj gamma ia xj. This means that gamma ia xj for all a is equal to g are eigenvectors of P with same eigenvalue Cj. Let there be m such independent eigenvectors of P having same eigenvalue Cj. But the eigenvectors B belonging to an eigenvalue generate a subspace Lm, which is invariant under G. Now, if Lm is a proper subspace of Ln, that is, if Lm is not the same as Ln, then Ln as an invariant subspace, gamma I must be reducible, which is contrary to the hypothesis. Therefore, Lm must be identical with Ln, making all the eigenvalues of P equal to each other and equal to, say, Cj equivalent to C, giving P equivalent to Ce. There is one more possibility in the above treatment, that is, the invariant subspace Lm may contain only the null vector. However, this case is excluded from consideration because if X is a null vector, it trivially satisfies the eigenvalue equation Pz is equal to Cz with an arbitrary eigenvalue C. Hence the theorem. For the second proof, we shall first show that any Hermitian matrix which commutes with every matrix of an irreducible representation is a constant multiple of the unit matrix. Let H be a Hermitian matrix which commutes with all the matrices of representation gamma I, so that H gamma I is equal to gamma I A H for all A belongs to G. Let U be unitary transformation which diagonalizes H, that is, U inverse HU is equal to HD1. UHD is equal to U inverse of H inverse, which HD is a diagonal matrix which diagonal elements say Di, which are the eigenvalues of H. Let us suppose the eigenvalues of H are not all the same. Let us pick up certain eigenvalue which is repeated, say k, once, where 1 less than or equal to k less than or is equal to n by a rearrangement of the columns of U. The order of the eigenvalues Di in HD can be changed at will. Let such a rearrangement be made to bring the chosen equal eigenvalues in the first k positions of HD, so that D1 is equal to D2 is equal to Dk is not equal to D nu. K plus 1 not is equal to nu less than or equal to n. Multiplying H gamma I A is equal to R gamma I A H for all A belongs to G from left by U inverse and from right by U, we have U inverse HU, U inverse gamma I A U is equal to U inverse gamma I into A, U inverse HU prime, or HD gamma I inverse A is equal to gamma I inverse A HD for all A belongs to G, where gamma I inverse etc. are the matrices of a representation equal to gamma I. Taking the j nu element of both sides, we find dj gamma j nu I prime A is equal to gamma j nu I prime A d nu. Dj minus d nu or j nu I prime A is equal to 0 for all A. It represents gamma I inverse, and hence its equivalent representation gamma I must be reducible. But by assumption, gamma is an irreducible representation, which is possible if and only if k is equal to n. That is, if and only if all the eigenvalues of H are the same. This shows that H is equal to HD and H must be a scalar matrix. Now let P be any matrix which commutes with all the matrices of the representation gamma I. Then by taking the Hermitian conjugate, we have P dagger gamma I dagger A is equal to gamma I dagger A P dagger, or P dagger into gamma I into A inverse is equal to gamma I into A whole inverse P dagger, or P dagger gamma I A inverse is equal to gamma I A inverse P dagger for all A belongs to G. Hence, P dagger also commutes with all the matrices of gamma I. We can define two Hermitian matrices H1 and H2 such that H1 is equal to P plus P dagger divided by 2. H2 is equal to I P dagger minus P divided by 2. P is equal to H1 by plus I H2. P dagger is equal to H1 minus I H2. If both P and P dagger commutes with the matrices of gamma I, equation 3.36a show that H1 and H2 also do. As just shown above, H1 and H2 must then be constant matrices. From 3.36b, it therefore follows that P must be a constant matrix, completing the proof. The importance of this theorem lies in the fact that its converse are also true. Thus, if no matrix other than a constant matrix commute with all the matrices of representation, then the representation is irreducible. The next is Schur's lemma 2. If gamma I and gamma j are two irreducible representations of dimensions Li and Lj respectively of a group G, and if a matrix M of order Li cross Lj satisfies the relation gamma I A into M is equal to M gamma j A for all A belongs to G, then either A M is equal to 0, the null matrix, or B determinant M is not equal to 0, in which case gamma I and gamma j are equivalent representation. It should be noted that true representation can be equivalent only if the dimensions are equal. Hence, if Li is not equal to Lj, only case A applies. The proof of Schur's lemma 2. Taking the Hermitian conjugate of both sides of 3.37, we have M dagger gamma I dagger A is equal to gamma I dagger A M dagger for all A belongs to G. M dagger or gamma I A inverse is equal to gamma j A inverse of M dagger for all is equal to G. Multiplying from the right side by M, we get M dagger gamma I A inverse M is equal to gamma j A inverse M dagger M for all A belongs to G, or M dagger M gamma j A inverse is equal to gamma j A inverse M dagger M for all A is equal to G. By using 3.37, thus the matrix M dagger M commutes with gamma j A inverse for all A inverse of G, and therefore by the previous lemma must be a constant matrix. M dagger M is equal to CE. We first consider the case Li is equal to Lj is equal to N. Say from equation 3.39 we have determinant of M dagger M is equal to determinant of M dagger determinant of M is equal to e power n 3.40. If e is not equal to 0, then determinant M is not equal to 0 because determinant M dagger is equal to determinant M conjugate. Therefore, M inverse exists, and from 3.37 we have gamma j A is equal to M inverse or gamma I A M for all A belongs to G, showing that gamma I and gamma j are equivalent representation. If C is equal to 0, then taking the I, I element of 3.39, we find summation of k M I k dagger M k I is equal to 0, or summation k gamma conjugate M conjugate of ki or M ki is equal to summation of k modulus of M ki square is equal to 0, which is possible if and only if M k is equal to 0 for all 1 less than or equal to k less than or equal to n, but I is arbitrary and can take any value from 1 to n, hence M is equal to 0. In the second case, when Li is not equal to Lj, we can assume without loss of generality that Li is less than Lj. We supplement the matrix M by writing Lj minus Li, rows of zeros, to give a new matrix M. It can be easily seen by matrix multiplication that M prime dagger M prime is equal to M dagger M, and hence determinant of M prime dagger M prime is equal to determinant of M dagger M, or determinant of M prime dagger into the determinant of M prime is equal to Cn. By using 3.40, here we have put Lj is equal to n. However, by inspection of 3.41, determinant M prime is equal to determinant M prime dagger is equal to 0. In C is equal to 0 and M dagger M is equal to 0. Once again, taking the I, element of M dagger M, we see that M is equal to 0. This completes the proof of the lemma. Schur's lemma states that if a linear map commutes with all operators of an irreducible representation, it must be either 0 if the representation are non-isomorphic, or scalar multiple of the identity if they are the same. The fundamental result has key application in quantum mechanics, particularly in angular momentum theory, where it explains why certain operators commute. It also plays a crucial role in character theory, ensuring the orthogonality of irreducible representation, and in matrix representation, where it helps classify central elements in group algebras. This seminar is done by me, myself, or Joseph Cesar Sandarkumar on Schur's Lemma 1 and 2. Thank you.